Hello everyone, welcome to this talk. My name is Liang, a postdoc from Argonne National Laboratory. Today I will present a paper named TopoSZ, Preserving Topology in Error-Bounded Lossy Compression. This is a collaboration with Liang from the University of Kentucky, Hanqi from the Ohio State University, as well as my PhD advisor Wang from the University of Utah. A scalar field assigns a scalar value to every point in the domain. This type of data may arise from scientific simulations or observations. In this work, we deal with both 2D and 3D scalar fields. Advances in high-performance computing allow researchers to generate extremely large volumes of scientific data. Such data pose significant challenges for memory resources and transmission bandwidths in scientific analysis and visualization. Lossy compression, which throws away some of the data in order to save space, is one of the ways to address this challenge. This slide lists some of the error-bounded lossy compressors. Here is an interesting picture. It visualizes data compressed by ZFP. From the left to the right, the compression ratio is increasing from 1 to 64. I think most of us cannot notice the information loss in the left part of the picture. This is the beauty of lossy compression. The compressed data can be significantly smaller than the original, much more than lossless compression. The downside is that the decompressed data is not the exactly same as the original. In order to control the amount of information loss, many scientific applications require an error-bounded control for lossy compression. For example, ZFP guarantees the point-wise error between the original and the decompressed data. However, can error-bounded lossy compressors preserve topology? Unfortunately, the answer is usually no. So what do I mean by topology? Given a set of scalar fields, topology plays an essential role in capturing the shape of scalar field data. It has found applications in visualization across the fields of structural biology, climate science, combustion studies, etc. The motivation of this paper is to develop a topology-preserving error-bounded lossy compressions for topology-based visualization. We are interested in preserving topological features captured by contour trees. Here is a simple example of contour tree. It captures the connectivity among level sets. Given a scalar field, we use a compressor to get the compressed data. So how to evaluate the performance of topological preservation? In our work, we require the contour tree that arises from the original scalar field and the decompressed scalar field to have the same structure. The main idea is to derive topological constraints for our compressor that can eliminate 3 topological force cases, including unexpected added branches, missing branches, and false types of endpoints of branches. Now we use the pipeline of our TopoSZ to highlight our contributions. Given a 2D or 3D scalar fields, first, we use a contour tree to derive lower and upper bounds as topological constraints for every point in the input domain. We call these steps the initialization step for our compression process. Second, we provide a customized error-controlled quantization strategy to incorporate the topological constraints into the data compression process. Third, we give a contour tree-based iterative strategy to refine a subset of lower and upper bounds for lossy compression. In this step, if no topological force cases are founded, our compressor ends its iteration. Otherwise, another iteration is needed. Next, I will give some technical details behind our topology-preserving error-bounded lossy compression technique. A contour tree can induce a complete partition of the original domain. Easily speaking, each branch can correspond to a topological region that maps to it. A regular point from each topological region should be bounded by the scalar values of the endpoints of the corresponding branch. For example, for x from the purple segment, which is now highlighted by pink, has a function value fx. Its lower bound should be fb, and the upper bound is fa. Actually, for all points in the highlighted region, they are all bounded by fa and fb. Some topological force cases can happen using the lower and upper bounds we introduced in the previous slide. Then, iteration is needed until no force cases are detected. Now we give an example where a missing branch is founded in the decompressed scalar fields. Let's zoom in on the region where the missing branch happens. Instead of using scalar values of the endpoints as lower and upper bounds, we divide the original topological regions into subregions, for example, into two subregions. Now, the scalar values of points from each subregion should be bounded by the minimum and the maximum value of the points in each subregion. In this example, points from R1 should be bounded by the minimum and the maximum value of R1. The main idea of our iterative strategy is to iteratively provide fine-grained controls of error bounds in topological region until no force cases are detected. Then, how to incorporate lower and upper bounds into the data compression process? We customize an error-controlled quantization encoders from SZ. Let's review this encoder first. Given a real value of the data point at a preset global error bound sign, SZ predicts its value using a Lorenzo predictor. Then, we generated a number of second phase predicted values. The distance between any two adjacent second phase predicted values is equal to 2 xi. Now, we have a set of intervals where the predicted values lies in the middle of them. When the real value, marked as the green point, falls into certain intervals, each predicted value can be encoded by the index of its corresponding intervals. In this example, SZ uses 2 to the power of m minus 1 as the quantization code of the original data point. Such an encoder ensures the difference between the original and the decompressed value is smaller than the presetted global error bound and saves space by saving just the quantization code. Now we customize it to encode additional topological constraints. Firstly, we set the distance between any two adjacent second phase predicted values to be xi. The predicted values that are close to the real value in both directions are considered as pointed out by the original errors. Then we also require the decompressed value bounded by the lower and upper bounds. In this example, the real value will have 2 to the power of m minus 1 as its quantization code. These slides show an overview of the experimental results in our paper. We ran experiments with 7 datasets using 5 evaluation matrices and made the comparison between 4 state-of-the-art lossy compressors that do not focus on topology preservation, and 1 lossy compression that also considers topology preservation. Our experiments include compression capability analysis, runtime analysis, compression performance with respect to iterations, parameter settings, and the size of datasets. We've also made a comprehensive comparison between our method with another topology-preserving lossy compression. For the time limitations, this talk will not cover all experiments. Please refer to our paper for all experimental results. Now, let's compare TopoSZ against other state-of-the-art lossy compressors that do not focus on topology preservation. This slide shows the rate distortion plot using the number of topological force cases as distortion matrix. Rate distortion is a widely used assessment metric in compression community, where rate represents the average number of bits in the compressed data. It's natural to see fewer false cases as the bit rate increases for topology unwell compressors. Since more bits to store the data, less information, including topological information, is lost during compression. But our TopoSZ compressor can guarantee no false cases occur with any bit rate. Now we use PSNR as the distortion matrix in the rate distortion plot. PSNR is the peak signal-to-noise ratio. A larger bit rate leads to less information loss and therefore a higher PSNR value. So we can see all curves have increasing trends in this plot. Under the same bit rate, a higher PSN value represents a better compression quality. We can see our TopoSZ does not have the best performance of rate distortion in terms of PSNR, but it is still comparable among state-of-the-art lossy compressors. According to these two rate distortion plots, TopoSZ has a slightly worse rate distortion in terms of PSNR compared to ZS3 and ZFP, but it outperforms all error-bounded compressors in preserving topology. There are many future directions. We would like to further improve our framework for large-scale data, such as parallelized contour tree-related computation. It may be possible to improve the computation efficiency by reducing the number of iterations to eliminate false cases using machine learning techniques. We are also interested in preserving topological features using gradient-based topological descriptors such as Morse and Morse-Mel complexes. Finally, we would like to thank our funding agencies. Thank you.